All right, so we are going to get started. Today we're going to talk about the types of electric materials, and we're going to talk specifically about conductors today. So as you know, like if you break up, you think about the types of electronic or electric materials. You think about conductors, and then you think about insulators. So let me know if you're able to see my mouse. Just give me a thumbs up. Okay, great. Yeah, we were having some issues with this last week. Okay, so we have different types of electric materials. Insulators, as you know, they do not conduct electricity. They're also called dielectrics. And conductors conduct electricity. So conductors, conductive wire, for example, has a concept called resistance. You know, a wire will have certain resistance. And insulators, when we're talking about dielectric materials, what electronic element are dielectric materials are used in? You can go ahead and put it on the public chat. Exactly. Great. Yep. So conductive materials are often used with in resistors, and dielectric materials are used in capacitors. So we're going to talk about both, and we're going to talk about the electromagnetics of both types of materials so that you have a really fundamental understanding of what is going on when you study resistance and capacitance in your circuits classes. All right, so let's start with the dielectric material. So a dielectric material is often used in a capacitor. So the two types of materials differ in what happens when a voltage is applied to them. So let's say we apply a voltage to a dielectric material. So we have just this dielectric material here, okay, and we apply a voltage to it. So what happens? So it turns out that, as many of you know, we've talked about this when we talked about capacitors last module, that what happens is that you get the polarization. Well, we talked about the idea that you get an electric field that develops, and you get a buildup of positive charge on the upper end of the plate and the negative charge on the lower end of the plate. The plates are metal, by the way, okay, and there's a dielectric material in between. So what basically the plates, ignore what happens at the metal plates for now, okay, because that's going to be the topic of when we get into capacitors. What we're focused on now is the material. How do these two different materials behave? So in both cases, we have a material, and then we have a metal plate on top and a metal plate on bottom, and the only purposes of those is to be able to apply a voltage to the material. Okay, so what happens when we apply a voltage to a dielectric material? We get an electric field in the dielectric material. We don't get current. That's the key difference. So what happens in a dielectric material, and we're going to talk about this more later, so I'm just giving a very simplified diagram right now, is there's an effect where the atoms polarize. Okay, the charges in the atoms actually polarize, and they align with the voltage that's applied to it. We'll talk more about that later, but the key thing that happens is that you get an electric field. The second important thing is that the charges are bound. The charges don't move. Otherwise, you know, we showed an example of what would happen if you had like a free charge in this electric field. The charge would start to move, as we talked about before. But in a dielectric material, all the charges are bound to the lattice, so they don't move. Instead, they polarize. And when they polarize, they create this electric field. And different dielectric materials have different degrees of polarization. We're going to talk about that later, but what we're going to talk about today in class is the conductor. So we have a conductive material. They're used to make resistors, they're used to make wires, to transmit electricity from one place to another. When you place a voltage over a conductive material, same as we did with the dielectric material, a very different thing happens. First of all, there's no polarization of the atoms, and secondly, the charges are not tightly bound to the lattice, they are mobile. So when we talk about metals, you know, you may remember from your chemistry and physics classes that we think of metals as atoms that are connected together through bonds, but the electrons are loosely bound to the lattice, so the electrons are free to move. So when you place a voltage across here, there's going to be an electric field like this, Okay, but there's also going to be a current. There's electric field and a current density, J. We'll talk about that in a second. So current density means there's moving charges. Okay, now instead of having, so there's actually going to be a charge that moves through the circuit here like this in the direction that I'm showing with my mouse, in this clockwise direction. Okay, that's what happens when you attach a resistive material or a conductive material to a voltage source. It looks like a resistor. There's a current that goes through it. So in the material, it turns out there's both a current and an electric field. In the dielectric material, there's only an electric field and no current. All right, so we're going to dive into the details of how a conductive material works today. So this is sort of a mind map of what we're going to be talking about with conductors. We can think about what happens when you apply a voltage to a conductor. So you generate an electric field within the conductor, and these are the different things that can happen. In one case, let's say it's not connected to a circuit. There's an electric field, but it's not connected to a circuit, so there can be no current flow. Then what will happen is we'll look at the electric fields within the conductive material, and it turns out that the electric field inside a conductor is 0 in that case. So we'll talk about that. Then we'll talk about what happens when the conductor is connected to a circuit. As I showed you before, you get current flow. And when you have this type of situation, you have electric field in the material, you have moving charges, and that is represented by something called current density. You also have the concept of resistance. The resistance has to do with how fast those charges move through the material. And then finally, there's a concept of power. So when you have charges moving through a material, it turns out that you dissipate power in that material. So we talk about Joule's law, P equals IV. We'll talk about that. So this resistance is Ohm's law, power dissipation is Joule's law, and these electric fields and current densities are part of Maxwell's equations. So we'll talk about all of those. Okay, so the goal really should be to get a fundamental understanding of what is happening inside a conductive material when you apply an electric field to it. All right, so we're going to talk about the simplest case here, the first one here where we have that you have no current flow, but you just have an electric field and a conductor in the presence of an electric field. So we're going to actually talk about charges. The electrostatic situation is when you do not have any current flow. So we can think about a very simple example is when we inject charges. Let's say we were to inject charges into a metal sphere like this. Okay, so the question that we're trying to answer first is try to get an understanding of the differences of an insulator and a conductor. One of the key physical principles is what's going to be talked about on the slide is that the charges actually move to create a zero electric field in the material. This can be explained actually very simply. So let's say we do a little thought experiment. Okay, so we decide that, okay, we have a metal ball. Okay, just imagine like a ball made of a conductive material. And let's say we just had the ability somehow, this is just a thought experiment, but let's say we had the ability to put a bunch of charges in the middle of that ball of charge. Okay, so what happens, if you have a bunch of charges near each other and the charges are the same type, what are those charges going to do? And what is the law that describes that? So you can go ahead and put this on the public chat. Okay, I see Pooja and Arad are typing, so we'll wait for them. Others, please feel free to add in. Okay, they repel due to Coulomb's law. Right. We talked about Coulomb's law that positive charges are attracted to, like charges repel, opposite charges attract. So in this situation, if we were to inject a bunch of positive charges in here, what would happen is that they would actually repel and spread out like this. So this is what it would look like. The charges would spread out like this. So I'll show you again in this animation. So watch this here. So the charges move outwards and they distribute themselves on the surface. Okay. No, so the key thing is, in a conductor, the charges are mobile. They are able to move, and because they're able to move, the force pushes them away from each other. Now, the way that you can think about it, if the charges want to be as far apart from each other as possible, guess what they're going to do? They're going to arrange themselves on the surface. Okay, and moreover, they're going to distribute themselves equally on the surface. There's going to be a uniform charge density on the surface when you have a uniform shape like this. Okay, this is simply because the charges want to be as far apart from each other as possible. Okay, so this is why in a metal sphere, when you charge it up, the charges all reside on the surface. There are no charges in the middle of the sphere. Now, one important implication of that, actually several important implications of that. First of all, there's a charge density on the surface, but the charge density inside the sphere, okay, this rho v that you see here, inside the conductor, the volumetric charge density inside the conductor is equal to 0, because all the charges are on the surface. And another important and very interesting implication of that is that the electric field inside the material is equal to 0. Okay, so this is interesting. You can kind of think about this. I think this is a good thought exercise to do. So I'll just draw this out here. Let's say we're at an observation point in the middle like this. Okay, and let's see what the electric field is going to be just qualitatively. So remember, when we do this thought exercise, we have to think about the contribution of every single charge. So we have 1, 2, 3, 4, I don't know, however many, like 12 to 20 different charges on the interface like this. We have to consider the contribution of each one of those charges. So let's look at this charge, for example. This charge is going to be emitting an electric field that looks like this. So the electric field due to that charge is going to be in the downwards direction. The electric field due to this charge here is going to be in this direction. Okay, so we looked at these two as our examples. But let's add another two charges to it. The electric field due to this charge here is going to point in the upwards direction. The electric field due to this charge here is going to point in the right-hand direction. So you can see that the electric field due to these four charges, actually when you add them up, they're going to cancel each other, and the total electric field is going to be 0 in the middle there. Okay, and it turns out this is the case regardless of whatever point you are within the sphere. And it doesn't have to be a sphere, it can be any shape at all. The electric field inside a conductor is equal to 0. Now, another way that you can think about this is that if there were an electric field, let's just say somehow you were able to get an electric field in a conductor, then the charges would move. And the charges would move in a way that dissipates that electric field. Okay, so if you have a perfect conductor, this is an important point, that if it's a perfect conductor, then the electric field inside the conductor is 0. The examples that I showed you here, this is a conductive material, but it's not a perfectly conductive material. So in this case, the conductive material can have an electric field, and it also has current density at the same time. So this is a slightly different case. You know, we're talking about a resistive, a partially conductive material, a resistor. It's not a perfect conductor. In a perfect conductor, the electric field inside is always 0. Okay, so another implication of this is that the voltage is the same everywhere in the conductor. In other words, everywhere on the metal, if you were to charge up a piece of metal by applying a voltage to it, then everywhere on that metal, the voltage is going to be the same. Okay, and that's because the electric fields inside the conductor are relatively small, or 0 in the case of a perfect conductor. All right, next, on the conductor surface, there's a surface charge density rho sub s. So that charge density is given in rho sub s, which is the units for this is coulombs per meter squared. Charge per unit area. and the electric field here is perpendicular to the surface. Okay, wherever you have these charges, you are going to have an electric field pointing away from that charge. And that's the reason the electric field lines point outwards. Now, if the question you might ask is like, why, okay, I understand that the electric field lines point outwards, but why are they perpendicular to the surface? Again, we can do a little bit of a little thought experiment there. Let's say we have a positive charge here, okay? So we're going to look at the contribution of these three charges. All right, so this positive charge is going to create an electric field pointed in the outwards direction. This positive charge is going to create an electric field pointing in this direction, and this positive charge is going to create an electric field pointing in this direction. Like we saw before, when you add up these contributions, the tangential components will cancel, but the orthogonal component will remain. Okay, so that's the reason why the electric field lines are always orthogonal and perpendicular to a metal surface. And this little rule, it turns out, is very useful in solving electrostatics types problems. Okay, for example, in a capacitor type situation where you have, two metal plates here like this, we always know that the electric field lines are going to be perpendicular to that surface, regardless of what type of metal it is, regardless of the shape and so on. It's always perpendicular. All right, so this is a good time to stop for some questions. Any questions on this? Okay, good. Okay, Ivan has a question. Good. Okay. You don't have to apologize. That's okay. If anyone else has questions, please, please let me know. All right. So a real life example of that you've probably seen in your physics type classes is this thing that's called a Van de Graaff generator, and it turns out October 2019. Which was, fairly recently, was the 90th anniversary of this really cool little device that demonstrates a lot of these principles. How it works, I'll just tell you how it works. So first of all, what it is that the Van de Graaff generator, it generates charge on the surface of a metal. And usually the metal looks like a big ball sitting on top of what looks like a pole or a stand. And there's a ton of charges that this generator builds up on the surface of the material. And like we said in class just now, that we said that the charges are all on the surface. They're not in the metal, they're on the surface of the metal. Because they're on the surface of the metal, when you touch it, your body is conductive, so those charges actually get transferred to you. And then your body is also conductive, so the charges on your body also behaves similar in some ways to a metal, is that you get a charge buildup on like on your head like this, and it causes your hairs to stand out. Again, we could actually go into a lot of details and talk about the exact physics of what exactly happening is all the electric field lines and such. We're not going to do that right now in the interest of time. What I would like you to know is a little bit about how the Van de Graaff generator works. Because it works on this principle of charge transfer and charge accumulation. It's a really neat little device. So let me just zoom in here like this and see a little bit about how this thing works. So the way, a Van de Graaff generator consists of a hollow metal sphere on the top here like this, and that metal sphere has this has a comb, which is a metal electrode, where there's a step which transfers the positive charges to the surface like this. Okay, and so that's the second part here. There's a metal comb, and the third part is a pulley made of acrylic glass. And what it does, it's kind of like a pulley transferring charges. So it works on this thing called the triboelectric effect, that charges are attracted more to a certain material than another material. And this is the way that you can transport charge from one place to another. So this pulley just goes in the counterclockwise direction, and as it's going, it is taking away positive charge from here and transferring positive charge up here like this. Okay, so the rubber belt carries positive charge to the sphere. That's number 4 on the left-hand side. And the number 5, this other belt, carries negative charge away from the sphere. Okay, the roller is made of metal, and it just it results in being able to build negative charge and transfer positive charge to the rubber belt. Rubber belt has the ability to attract positive charges more due to something called the triboelectric effect. All right, and because of that, what ends up happening is that you have a positive charge buildup on the top end of the pulley, and that gets transferred to the metal sphere. On the bottom end of the pulley, you have a buildup of negative charge, and that negative charge is either connected to ground, or it can also be connected to a little pole like this, so that you can have another metal ball with a bunch of negative charges on it, and you get, as you know, between positive and negative charges, you get an electric field line that points from one to the other. And you can make this electric field so strong that you get dielectric breakdown, and you get essentially a lightning bolt that strikes between the positive and negative ends. Okay, this is all due to electrostatics, but I bring this example up because it does show the importance of this concept of charges building up on the surface of a metal rather than inside the metal. And that's the reason this effect happens. All right. So just quick questions to make sure we're all here. So in this example, we have conducting spheres. Suppose we deposit a charge Q on a sphere with radius A. What is rho sub S? So you have 5 choices. I'm just going to start the poll here. Okay, start a poll, and there are 1, 2, 3, 4, 5 choices. So I will put this up here, and you can go ahead and put in your answer there. And we'll just wait for most of you to respond. All right, looks like we have everyone. Okay, I'm publishing these polling results, but unfortunately it doesn't look like you can see them. So I'm just going to read to you what the results were so you have an idea. 50% of you said A, and A is the correct answer. 8% of you, 2 of you said B, 6 of you said C, and then 2 of you said D, and nobody said E. All right, so A is the correct answer here. Oops. And let's just quickly look at why. All right, we deposit a charge Q on the surface of a metal sphere. So these charges distribute themselves equally on the surface of the sphere. All right, and if we want to find out the charge density rho sub S is equal to the total charge divided by the area on which the charge is distributed. So the area of a sphere is 4 pi r squared, so this will be q over 4 pi a squared. Okay, the answer is not 0 because the charges do distribute themselves on the surface, so you will have a surface charge. It is not equal to q over a because, again, because of this formula, it's q over capital A, which is q over the area. So let me just clarify that here. Total charge divided by the surface area of the sphere. Okay, and these other answers similar. Charges are distributed equally over the surface. All right, so the next question is, what is the electric field at a radius r? And again, I'll give you several minutes to do that. And again, you'll have 5 possible answers here. And the hint I'm going to give you here is that you can actually look back to some of your older notes and to find the answer to this. All right, when you think about what happens when you have a charged object. What is the electric field resulting from the charged object? Okay, let me clarify one thing. We are looking for a radius r outside the sphere. Outside the sphere. Oops. Okay, let's just wait for one more. Okay. All right, so it seems like most of you have answered now. Yep, so 14 of you said C, 4 of you said B, 1 said A, and 1 said D. The correct answer here is C. All right, and outside the sphere, what you can do is just look back at Coulomb's law. So we're gonna just go back here. In Coulomb's law, we talked about the electric field due to a point charge. Okay, when you have a sphere of charge like this looks very much like the point charge with a certain amount of charge Q. All right, and the electric field due to that is Q over 4 pi epsilon r squared. So that's where that is coming from. All right, now I'm going to ask this question again. A second here. Now one more time we'll do this. And this time we're going to do inside the sphere. So inside the sphere, what is the electric field? All right, let's just wait for a few more. Okay, good. Yeah. Okay, good. So it says 8 of you said A, 11 of you said B, 3 of you said C, and none for the others. So it seems like there may be some confusion between A and B. So let's walk through this. The correct answer is actually B. Right, and the simple reason for that is that, as we said on the last slide, the electric field inside a conductor, this is inside the conductor, everywhere in here, the electric field is equal to 0. So at any point R that's less than the radius of the sphere, the electric field is equal to 0. So this is the correct answer here. So all these other ones are not the correct answer. If you have electric fields can emerge in materials, like when you have, if the material is not a perfect conductor. Okay. All right. Any questions on that? Let's go back to the public chat and see if there's any questions on that. Let's see. Okay. No questions. All right. Is this making sense? Give me a thumbs up if it is, and if there's not questions. Okay, good. All right, let's move on then. So now what we're going to do is we're going to look at the second case. So what happens when you have a conductor that's connected to a circuit where you have current flow? So we're going to look at all these different things: electric field, current density, resistance, power dissipation, and so on. So let's just jump ahead there. All right, so the very basic concept, I like to start from the really basic concepts, is that you have a conductor with current flow. You place a voltage over a conductive or partially conductive material, like a wire like this. Let's say we have a wire that's made of copper, the kind you guys use in your lab. You are going to get a current. All right, and the current in this case is going from left to right. Why is it going from left to right? Well, the voltage source is positive here and negative here, so this is your positive end, and then this is your negative end. So in a resistive material, your electric field is in this direction, and that causes charges to move. We'll go over that in a second. All right. So again, just to clarify, so there's no confusion about this electric field issue, in a perfect conductor, the electric field is very near or equal. In a perfect conductor, it's equal to 0. In a very good conductor, the electric field is near 0. And in a resistive type material, you can have an electric field like this. Okay? So the current is defined as going from the positive voltage to the negative voltage. So this is the positive voltage on this side, and then here's the negative voltage on this side. So so your current flows from left to right. The units for current, just to remind everyone, is in amps, and 1 amp is 1 coulomb per second. All right, so that means like if you assume that there's 5 amps of current that's passing through this wire, that means there's 5 coulombs of charge passing through the wire's cross-section every second. And remember, one electron has a charge equal to 1.6 times 10 to the negative 19 coulombs. Okay, so 1 coulomb is a lot of charges, considering a single charge only has 1.6 times 10 to the negative 19 coulombs. Okay. All right. So let's now talk about the concept of current density. Okay, when we talk about currents in our circuits classes, we talk about the total current going through the wire, and the total current is what you can measure through an ammeter. But the concept of current density is what becomes important in electromagnetics, because especially when you have wires of different cross sections. So let's define what current density is. Current density is the concentration of moving charges at any given point in the cross section of the wire. Okay, and the reason we have current density is because some places can have more concentration than others. This is a really simple example where you have a wire of uniform cross-section, and the current density is, depending on the wire, actually, it may or may not be, may or may not be the same everywhere. Okay, the way that I've drawn it here, I've drawn it for simplicity's sake, that the current density is the same everywhere, meaning like the concentration of current is similar everywhere in the wire. But if you read through the, if you know how wires work, actually it turns out that most of the charges are actually near the surface. And so there's higher current density on the surface of a wire than there is in the middle. Okay, so that's the reason we need this concept of current density, because you can have a higher current density in some places compared to others. Another example is if you have a wire of differing cross section. So let's say in electronic circuits, what often happens is you may have a trace that looks like this, a big wide trace, and then in some parts of the printed circuit board, because everything's like super dense, you have to make that trace a little bit smaller to connect to one of your electronic components here like this. Okay, if some of you have done printed circuit board design, you'll know exactly what I'm talking about. And so wherever you have a situation where the wire or the copper trace narrows like this is going to have a wide cross-sectional area. This is going to have a small cross-sectional area. So this is literally like water flowing through a pipe. I want you to really, guys, think about current in terms of water flowing through a pipe, because it's very, very, very similar. When water flows through a pipe of large cross-section, there's it's moving at a certain velocity, and then when it's moving through a more narrow portion like a nozzle, it has to move at a faster velocity. Now, in the case of the electrical circuits, what happens, the velocity actually stays similar, but you have different current densities. Okay, and when you have different current densities, so let's say I have 4 arrows here. Okay, 4 arrows represent a certain number of electrons flowing through. In this narrow portion here, I still have 4 arrows here. Okay, remember Kirchhoff's current law that says like whatever current you have here, that same current has to be flowing through here, right? That's what Kirchhoff's current law says. So however many charges we have that's flowing through this portion of the pipe, which is wide, or this portion of the trace, the same number of charges are moving through this as well. So you can see here that the current density is higher. Okay, so that's the second example. The first example, as I said, was in a lot of copper piping. There's a higher charge density on the outside of the copper pipe, so there's a higher density of current, higher current density near the edges compared to the middle. Okay, so for this reason, if we really want to look at current, we can't assume that the current is uniform density everywhere. Okay, we'll have some simple problems where we do that, but in the general case, we cannot assume that. And that's what's being said here. If J is the same everywhere in the cross-sectional surface, then the total current I is equal to J times A, where A is the cross-sectional area of the wire. But in the more general case, when you don't have uniform current density everywhere, you have to calculate the total current by using an integral. Okay, and this is a surface integral. So if we want to be totally clear, we can add a second integral sign here to indicate that this is a surface integral. Or you just put the S here like this, and that indicates that it's a surface integral. Or the fact that you see a ds here instead of a dl, that means it's a surface integral. So the surface that you're going to integrate is the cross-sectional surface of the wire here like this. Okay, so this is ds. Right, and the direction for the ds vector points orthogonal to the surface. So this way you know what type of, what the orientation of ds is. So you'd figure out J, you'd figure out ds, and then you figure out the total current this way. All right, so let's do a very simple example, uniform current density. Suppose that I have a wire of uniform cross-section. The wire has a radius of 5 millimeters. What's the total current? Okay, so assume we have a wire like this. The wire has a radius of 5 millimeters, and we have uniform current density running through it. J equals 0.1 amps per millimeter squared, and so please calculate the total current here. We'll put out a poll here. Let's give you a hint here. Oops. Uniform current density. In the case of uniform current density, I is going to be equal to J times the cross-sectional area. Okay, so this one, it actually looks like we have some confusion here. All right, so there's 3 of you said B, 7 of you said C, 9 of you said D, and 2 of you said E. So most of you actually put D. D is actually not the correct answer, unfortunately. It's actually B. B is the correct answer. So for those of you who put D, I actually want to see, since most of the class, it seems 10 of you had put D. So I would like to see what was, if you could put out here in the public chat, what was the logic there? Because I just want to make sure that everyone is understanding the concept. Five squared times pi, okay. Okay, forgot to compute the area and use radius instead of area. Okay, okay. Oh, answer too quickly. So let me ask you all, is this, am I giving you too little time, or are you feeling like pressure to just answer like right away and just know it off the top of your head? Should I give you guys more time and maybe have fewer of these poll questions? Because the whole purpose of this is just to keep everybody actively doing something, because otherwise you're just sitting back on a couch and watching, just watching TV. I'm doing this to try to make you all more active in while we're doing the lecture. So I want to get everyone's feedback, because this is all an experiment, Okay, Cassandra says, I think you give us sufficient time. Good. Time is good, Falak says. Okay. Yeah, Hamza, thank you. The polls help. Okay, good, good. We'll keep doing this then. So here what we want to do is, So J here is 0.1 amps per millimeter squared. I'm going to actually put the units. If I don't put units, then just assume I'm using MKS units. So the area here is pi r squared, so pi times 5 millimeters squared. All right, and if you do the math here, it comes out to 7.9 amps. Okay, so it's just a question of multiplying by the area. All right. John, okay, thank you. So the time is okay. Good. If anyone has individual concerns about that, please let me know. Okay, suppose we have a wire with non-uniform current density. All right, the wire is on the z-axis, and the current density is given by J of R is equal to 5R. So let's say we have cylindrical coordinate system, wires on the z-axis like this. And this example is the one that I was telling you about earlier, is that your current density might actually be larger on the outer parts than it is on the inner part. So in this example, it's showing you J of R is equal to 5 times R. So the current density in the middle is actually 0, but the current density on the outside is largest. Right? So you have a situation where your current density in the middle of the wire is small, and the current density on the outside of the wire is large. It's a function of R. So in this case, what is the total current in the wire? The radius of the wire is 1. So I don't have a multiple choice thing here for this, so this is one that I'd actually like to go over step by step, and I think we can fit it right here on the slide. So here's the formula that we're going to use. I is equal to the integral of J dot ds. Okay, and we're integrating over a surface. And just like before, I like to use a very step-by-step methodical approach to doing these integrals. So our first step, we're going to find ds, then we're going to find out what J is, and then we're going to find the limits of integration, and then actually do the integral. So let's start with J. Okay, J is equal to 5R. And the direction of J is going to be in the z-hat direction, okay? Because we're in the cylindrical coordinate system here. Second step is to figure out d sub s, or ds, sorry. So the ds we have to draw out. We know that it's the ds is orthogonal to the direction that the current is moving. So if it wasn't clear from what I said earlier, the cross-sectional area is orthogonal to the direction the current is moving. So the area here, in this case, the cross-sectional area would be just, let me put this in blue here, it would be this surface here. Okay, so d sub s has magnitude, and it has it has magnitude and direction. So ds in this case is going to be, we're integrating over the surface of this disk here. So the ds is going to be r dr d d phi. Okay. There's no, we're integrating over the r-axis, and we're integrating over the phi axis. Okay, and this is going to be in the z-hat direction, because the surface, the vector that's perpendicular to the surface is in the z direction. All right, so step 3, the limits of integration. So if we want to integrate over this disk, is r is going to go from 0 to 1. Okay, and phi is going to go from 0 to 2 pi. Okay, and the fourth step is where we just do the integral. So I is equal to the integral from r equals 0 to 1, phi equals 0 to 2 pi of j dot ds. Okay, now j is equal to 5r times z hat, ds is equal to r dr d phi z hat. So you take the dot product of these two, they both have z hat components, so the dot product is just 5r times this. So you get 5r squared dr d phi. Separate out the variables. So you get phi equals 0 to 2 pi d phi, and then the integral from r equals 0 to 1 of 5r squared. You could take the the 5 out if you wanted to, but we're just leaving that here. Okay, so here you get 2 pi, and here you get 5 over 3 r cubed evaluated, 5 over 3 r cubed evaluated from 0 to 1. So you just get 2 pi times 5 over 3 times 1 minus 0, which is 1. Okay, so then this is then equal to 10 pi over 3 is the current. Okay, so again, strategy is to figure out what your current density is, and this was given to us in the problem. Second step is to figure out what your ds is. It has to be orthogonal to the direction that the current density vectors are moving. Step 3, you figure out the limits of integration. So you want to cover the entire cross-section of the wire. And then step 4, do the integral to figure out, to find the current, the total current. Questions? All right, good. All right, let's get into talking about drift current now, the movement of charge due to an electric field. So we're going to look a little bit more at the details of this, in case you're wondering, like, what happens when charges, how do the charges move? Why do they move? What's going on in the material? This is one way to think about it. So let's say we have a wire, let's say a copper wire like this. It has it's not a perfect conductor, so it's going to have some resistance associated with it. So the type of current that we're talking about is drift current. There's actually another type of current called diffusion current, which we talk about in the semiconductor class and has a very important role in diodes. And so we're not going to talk about diffusion currents. When we talk about Ohm's law, the typical V equals IR, that's drift current that we're talking about. And this is how it works. Imagine that you have just a material like this, like a copper resistive material that's not a perfect conductor. You put a voltage across there. The applied voltage is going to generate an electric field. Now, the general formula for electric fields, E is equal to negative del V. Okay, in this particular case, in really simple circumstances like this, it turns out that this simplifies to V over the length L. Okay, but this is the general formula. Okay. So the point is to get a qualitative feel for what's happening here. So what happens is when you place a voltage on there, these typical metals, they contain electrons. And they contain electrons at some charge density. The units is given in coulombs per meter cubed. Very conductive metals will have a high charge density, and lower conductive metals will have a lower charge density. So I'm just going to put this out here like this so you can see have some animations here. So start here at the top. The applied voltage generates an electric field. So the electric field is pointing from positive to negative. So the positive side of the material to the negative side of the material. Okay, and that electric field is approximately equal to V over L in the case where you have a material with uniform properties, uniform cross-section. But this is the one that you want to remember. This is the general definition. Okay, so this material contains charges in here. As I said, these most metals contain electrons that are loosely bound to the lattice. So these electrons can actually hop back and forth from state to state, so they can move. And that's what really makes the material conductive. The electric field pushes the electrons in a direction opposite the electric field. So the electric field is pointed from right to left, and so the electrons are going to move from left to right. They move opposite the electric field. If there were positive charges, they'd move in the same direction. Right. Okay, so electrons, the way they move is actually pretty complicated. It's kind of like the electrons are moving, they bump into something, they bump and they go in the different direction, and then the electric field pushes them back, and then they bump again into an atom, and then they move back. So these electrons, it's not a smooth motion. They're always colliding with stuff. But on average, there is an average velocity from left to right. Okay, so that average velocity can be calculated using this equation. U is equal to mu times E. So the electric field was generated by the voltage, so that's our E. And now the velocity that these electrons move is given by the mobility times E. So the mobility is a material parameter which describes how easily the electrons move through it. A material that has high mobility, it means that the electrons don't bump into things as much. Okay, this is why like vacuum has a really good mobility, like out in space. Things can move very, very rapidly because there's nothing for the electrons to bump into. All right, so the charges that are given off by the sun, for example, these things are moving super fast, and they can move super easily because there's nothing that they're bumping into. But in a metal material, the electrons are bumping into atoms, and they're scattering, they're changing directions, but then they're being pulled back by the electric field. So the higher the mobility of a material, the more easily the electrons can move through it. Generally, higher mobility means fewer collisions. And a lot of superconducting materials have very, very high mobility. The concentration of moving charges is called current density. So when these charges are moving, you can calculate the current density by looking at the charge density, rho v, multiplying it by the velocity at which they're moving, mu. And so the formula for current density is actually quite simple. Charge density times mobility times the electric field. Okay, so this connects to the concept that we talked about on the previous slide. How do you actually find the charge density? Amps per meter squared is the units for charge density in the MKS system. Then the next step, if you want to find the total current is the total number of electrons passing through the cross-sectional area per second, and as we showed in the examples, the total current is equal to the integral of J dot ds. This is integrating on this cross-sectional area that you see here. Okay, you're just counting up the number of electrons that are passing through that area per second. Okay, and some more things about the units and here for your reference in the notes, but the main concepts we've gone through. Now let's talk about semiconductors. One of the important differences between metals, which you see here, metals have just electrons, but semiconductors can have two types of charges, electrons and holes. All right, and it turns out that you can have both play a role in the conduction. You place an electric field over a semiconductor, just like before. You put a voltage source across there, and it turns out the positive charges, positively charged carriers, which are called holes, they move in the same direction as the electric field. The negatively charged carriers, in other words, the electrons, move opposite the electric field. And so now you have two types of carriers. You have to take both types of carriers' effects into account. And so your velocity, you can think about, this is for a single carrier. This is for the case of a metal. If you remember, in the previous slide, we found that the velocity of the electron is equal to mu times E. The current density is equal to the charge density times the mobility times the electric field. And so this charge density times the electric field, these are both material parameters. Okay, rho v and mu e, these are both material parameters. So one of the things that we do to make it simple so that you don't have to know these two constants for the materials that you're working with, we lump both of these constants into a single parameter called the conductivity, sigma, given by sigma here. So sigma is equal to, for a single charge carrier, it's equal to rho v times the mobility mu. Okay, so this is the conductivity. Let's write this down. Conductivity of the material. Intuition here is that the more charges a material has, it'll be more conductive. The faster the charges can move through the material, it'll be more conductive. Okay. Now, in the situation in semiconductors, when you have two charge carriers, you have to consider the motion of both types. So there's a velocity of the electrons given by mu sub e times the electric field. There's a motion of the holes represented by mu h times the electric field. Notice that there's a negative sign here because the electrons travel opposite the field. The total current density, you just add up the two contributions. This is the current density due to electrons. This is the current density due to holes. And you can take this and you can also put this in the same form of sigma times E. So now your sigma has two components to it. So in the case of a metal, the sigma you only had to consider the density and the mobility of the electrons. In the case of the semiconductors, now you're considering the density and mobility of the electrons, and you're adding to that the density and the mobility of the holes. So both have to be taken into account with semiconductors. So in summary, with metals have only the electrons as a type of charge carrier. Your sigma is equal to Q times mu n times n. In a general semiconductor, when you have holes and electrons, it's equal to the formula I just showed you. You have to account for the electron and hole concentration. In an n-type semiconductor, where you have electrons and holes, but you have so many more electrons than holes, then your sigma is going to be equal to Q times mu n times n. And in a p-type semiconductor, when you have many holes and very few electrons, the conductivity is Q mu p times p. Okay, so depending on the type of material that I give you, you're going to be using the appropriate equation. Here are some of the conductivities of common materials. So if in these types of questions, I could ask you to calculate the conductivity of the material if I'd like. In other problems, you're going to be given the conductivity, and you could just look it up on a chart like this. These are some conductivities of materials, just to give you an idea of how much the conductivity can vary for the different types of materials. So in a perfect insulator, the conductivity is going to be 0. It does not conduct electricity at all. The current densities are also going to be 0. In a perfect conductor, the conductivity is going to be infinite. There's no material that has infinite conductivity, but superconductors have really high conductivity. And the electric field is going to be 0. So you see the analogies between the two. In a perfect insulator, the current density is 0. In a perfect conductor, the electric field is 0. So let's look at some of the common materials. Silver, copper, and gold, and aluminum. These are all used in certain types of electronic circuits. Copper is the most commonly used, I would say. Gold is used in some type of semiconductor materials. Silver and aluminum are also common types of materials that are used in science and engineering. I'd say copper is probably the most used in electronic circuit boards. A slightly less conductivity than silver. Gold is slightly less than copper. Aluminum slightly less than that. Materials like iron and mercury have high conductivities, but things like, these are harder to work with. This is a magnetic material, and mercury, as you know, is quite toxic. There's been a lot of interest in carbon type materials. Carbon on its own, like the carbon, like the soot, or like the shavings from a lead pencil, like maybe 3 times 10 to the 4th. I'm sorry, shavings from a carbon pencil, not from a lead pencil. Fairly low conductivity, but there are new materials like graphene, for example, a special type of carbon, which is a two-dimensional carbon, which has very high conductivity, and we're able to use those materials now for conductors instead of the common metals that we've been used in the past. Semiconductors, silicon has low conductivity. Semiconductors are neither an insulator nor a conductor. It's somewhere in between. There's a huge range of conductivities you can have with semiconductors depending on how you dope the material. So if you want to know more about that, we talk a lot about that in my other class, 4570 and 5550. And if you're really interested, the lectures for that are also out on YouTube. And you can watch it, on your lockdown, since you all have all this extra time. No, I'm joking about that. A lot of students have been telling me they're actually more busy during the during this lockdown than they have been in the past. So insulators have really low conductivities, -10, -12, -17. Okay. All right, let's go back to basics now, and let's talk about the concept of resistance. All right, we've talked about current and current, voltage, conductivity. Now let's talk about the concept of resistance. And you all know this relationship, V equals IR. So I think that's the thing that we want to start with. You put a voltage across a resistor, you get a current running through there, and V equals IR relates the voltage, the current, and the resistance of the resistor. So we're going to go into more details of that now. Now, physically, what I'd like you to think about, this is actually a cartoon that one of the previous students actually shared with me that I thought is really illustrative of the concept of electrical resistance. Voltage generates an electric field, and the voltage pushes the charges through the material. All right? So the higher voltage you have, you're going to have more force pushing the charges through the material. Okay, so you can think about volts as a force that is pushing the charges through the material. The amp, the way you can think about amps is coulombs per second, so it's moving charge. Right, the voltage is pushing the charge is trying to go through the wire. Okay, but let's say you have, if the wire is very, very large, very, very wide, the charges can move through there very easily. But if you have a constriction in the wire, if you have a narrow region of wire, that narrow region has higher resistance. Wherever you have higher resistance, it's harder for those charges to move through the wire because more charges have to squeeze through a small area like this. Okay, so the way that you can think about resistance is how much you're squeezing the charges, how concentrated the charges are in a certain area. Out here, the amps would be moving easily, but through this constriction zone, the charges are squeezed together, so there's more resistance, and that's why this area has more, this area, the small section of the trace has more resistance associated with it. Okay, all right. So let's look at an example of a conduction in a copper wire, and there's a 2 millimeter copper wire with conductivity 5.8 times 10 to the 7th Siemens per meter, mobility equal to 0.0032 meters squared per volt second. A 20 millivolt per meter electric field is applied, and we are going to find the following things. We're going to find the volumetric charge density, find the current density, the current flowing in the wire, the electron drift velocity, and the volume density of free electrons. Okay, this one, instead of drawing it out for you all, I actually have the solutions here from one of the textbooks that we use in the class. So I want to walk you through each part of this and what the strategy is, what the logic is, but we have for our reference the solutions here. All right, so let's start by I always like to start with drawing a picture. All right, so you draw a 2 millimeter copper wire like this, and it has a certain conductivity. So we can say sigma is equal to 5.8 times 10 to the 7th. And the mobility is given, and we're applying a 20 millivolt per meter electric field. So E equals, E is in the left to right direction, and it's 20 millivolts per meter. This electric field is going to cause the charges to move. Okay, copper means it's mostly electrons, so we can think about the electrons moving in this direction. Let's just draw a bunch of electrons here like this. The electrons are moving in this direction, opposite the electric field. So I'm going to just erase this here. So we're asked to calculate a whole bunch of different things. Okay, the mobility, mu, oops. 0.0032. Okay. Now, most of the time, I would always want you to put units down here. Okay, and in an exam, that's what I would expect. However, in this, if you're working with MKS units, okay, most of the things that we're working with here is MKS units. You know, sometimes I don't put the units here. If we're working with anything other than MKS units, the units have to be there so that you understand. For example, here we're given 20 millivolts per meter. That's not an MKS. So I'm just explicitly saying that there. All right. So the first step is to find the volume charge density. And the way you do that is you have this relationship we found before, that the sigma of a material, sigma is equal to rho VE times the mobility. Okay, we saw that a few slides ago. How conductive a material is depends on how many charges you have in there, multiplied by how fast those charges move through the material. All right, so to find, we're given the mobility in this problem, so we're just solving for the charge density. So sigma divided by the charge density, you're given the sigma in MKS units, the mobility in MKS units, and you come up with the charge density. And the units for charge density is coulombs per meter cubed. Okay, so the second thing that's being asked is calculating the current density. The current density can be found, as we said, the current density is sigma times the electric field, and sigma is given by this definition up here. Right? So sigma, we're given in the problem, is 5.8 times 10 to the 7th. The electric field is 20 times 10 to the negative 3. Where is this negative 3 coming from? This is 20 millivolts per meter. So this is equal to 20 times 10 to the negative 3 volts per meter, which is the MKS units for electric field. Multiply these two together, you get 1.16 times 10 to the 6th amps per meter squared. Okay. Next part, find the current flowing through the wire, 3.64 amps. The way that we find the total current is we multiply J times the cross-sectional area. Now I just want to note here that I always start with this one. I is equal to the integral of J dot ds. That is the general formula for current. In the case where the current density, okay, wait, hold on, J times the current density, we found the current density based on the electric field. The assumption in this problem is that the current density is uniform, and when the current density is uniform, I is equal to J times A. This is for uniform J across the cross-sectional area. Okay, that's why they're using this formula I equals J times A. So this is equal to J times pi d squared divided by 4. Okay, this is because you have this 2 millimeter copper wire. All right. Excuse me for a second. The current density is given by 1.16 times 10 to the 6th, and then pi times 4. You substitute pi d squared in here, and you get 3.64 amps there, total current. By the way, but this 4 here, instead of using pi r squared, they're using pi d squared, and that's why they have the 4 here. R is equal to d over 2, you square it, you get d squared over 4. All right, next part here is you're asked to find the velocity of the velocity of the electrons. How fast are these electrons moving through the wire? It's also a fairly straightforward problem. The velocity, as we found, is a mobility times the electric field. Multiply the two together, you get negative 6.4 times 10 to the negative 5 meters per second. 10 to the negative 5 meters per second. So the electrons are actually moving quite slowly through the material there. So if you ever wonder, when you guys talk about current in your circuits classes, how fast are the electrons actually moving through the copper wire? Well, in this particular case, they're moving really, really slow. Okay, less than a tenth of a millimeter per second. Okay, the minus sign indicates that mu e is in the direction opposite the electric field. Generally, left to right means positive, right to left means negative. And the last one here is find the volume density of free electrons. And this one we can find by taking rho VE divided by E. So let's try to understand what's going on here. Volume density of electrons is equal to the number of electrons per unit volume, so per meter cubed. All right, it's not asking for charge density, it's volume density. It's the number of electrons per meter cubed. So the way that you figure out number per meter cubed is you take rho VE and you divide it by E. So this should make sense because rho VE is coulombs per meter cubed. And the units here, this is the amount of number of coulombs for a single electron. So this is, the E is equal to 1.6 times 10 to the negative 19 coulombs. All right, you take coulombs per meter cubed, divide by coulombs, and you get 1 over meter cubed. So that's the units, that's actually the units for volume density. Number of electrons per meter cubed. All right, so keep that in mind if you have problems like this in your homework. Just divide rho VE divided by the charge for a single electron, and that gives you 1.13 times 10 to the 29th electrons per meter cubed. So this is how many electrons you typically have in 1 cubic meter of material. That's a lot of electrons. All right. Let's do another problem here. For free charge density of 0.3 nanocoulombs per millimeter cubed in a vacuum tube for a current density of negative AZ equals 2.4 amps per millimeter squared. Find the total current passing through a hemispherical cap specified by R equals 5 millimeters. So this is a tricky problem that I think that we'll have to do in the homework, or maybe come back to later. I want to actually go on right now and talk about the electrical resistance. Okay, we'll come back to this later if we have time. Actually, I think I would prefer to have this challenging problem as one of your homework problems. So let's talk about electrical resistance now, because we have some time left in the class. So the general definition of electrical resistance is the ratio of voltage over current. So the way that resistance is defined is R equals V over I. Hold on. Where's my mouse? Oh, that's weird. You all can see my mouse on the screen, but I can't see it here. So, okay, give me 1 second here. Okay, now you all should be able to see my mouse. All right, the general definition of electrical resistance is the ratio of voltage over current. So this is Ohm's law, right? So what we're doing now is we are taking Ohm's law and we are going to define it in terms of integrals. Okay, this will actually allow us to derive the resistance of a material that has a unique or interesting type of geometry. All right, so it looks like we have about 10 minutes to cover this. I think we can do it. All right, so this is the strategy for solving these problems is to do voltage divided by current, and this is how you would solve the problem. To find the voltage, you have to take the integral of E dot dl. This is another definition. This is the definition for voltage that we found in the electrostatics chapter. And for current, you have to do the integral of J dot ds. So it turns out that both of these can be put in terms of the electric field. Obviously, at the top here you have, this is the integral of E dot dl, but J is equal to sigma times E. That's the definition of the current density. So now you have something that's in terms of the electric field on top, and you have something that's in terms of the electric field on the bottom. So what you can do then is you can figure out the resistance of a material by performing two integrals, one to find the voltage and then one to find the current. And I want to show you how that can be done really simply. So the voltage across the material can be performed by performing a line integral in the direction of current flow, and the current I can be found by taking a surface integral in integral of the cross section. All right, so our strategy here, calculating the resistance of a wire of length L and a cross-sectional area A. So as many of you know, the resistance of a wire like this is L divided by sigma A. But did you ever wonder how this formula came about? So we're going to derive this formula really quick right now. RE equals L divided by sigma A. Our strategy is to find J and E, and then the next thing we do is find the voltage V, and then we find the current I, and then we just take the ratio of V over I. So essentially we're using this strategy, ratio of V over I. Okay, so let's go through this, and I'm going to show you how to do this. Again, this is just a simple wire. X-axis is where the direction the current is moving. The ds is the disk here, and ds is perpendicular to this. So I'm going to pull up my OneNote here and just show you really quick how to do this problem. So you have a wire here like this. You know, the cross section looks kind of like this. ds is pointed in this direction. All right, so our strategy is to find J and E first. So what we want to do is, what is the resistance R? Okay, the electric field is pointing in this direction, and so our current is also in this direction. Okay, and we are orienting ourselves that this is the X direction. All right, so we are going to say that the first step is to find J and E. So we're going to say E, the electric field we know is going to be pointed in from left to right, so it's going to be EX times X hat. Okay. And the current density J is going to be sigma times EX times X hat. Okay, just from the definition of current density is equal to the conductivity times the electric field. Okay, so now the next step here is to find V. V is the negative integral of E dot dl. So V equals the negative integral of E dot dl. All right, now we have an integral to do, so we have to think about, okay, what is our E, what is our dl? We already found the E up here, so we're kind of done with that. So our dl, so let's write that down. dl is equal to, we're moving in the x direction, okay, along the x-axis. So the dl is just x hat times dx. Okay, if we're in a cylindrical coordinate system, we'd have to make sure that we have the correct dl values, and this Cartesian is very straightforward. So our dl, we have our dl here, we have the E. Now, now we have to think about our limits of integration. The limits of integration is going from x equals 0 to x equals L. So that's our limits of integration. So integral, we're going to integrate from x equals 0 to L. All right. So our voltage is equal to the negative integral from x equals 0 to L of E dot dl. Okay, so our E is Ex times x hat. Our dl is x hat times dx. So when you take the dot product of these two, you just get Ex dx. Okay, and the electric field, we are assuming that the electric field is not changing as you move from left to right. It's a constant electric field. And so when you do that, then you get the integral of x, the integral of dx is equal to x, and this becomes Ex times L. Okay, so hopefully everyone sees how I got that. There should be a negative sign here. All right. Third part here is we're going to find I. We're going to find I. I is equal to the integral of j dot ds, and this is a double integral. So to figure out the integral, we start by figuring out what ds is. So ds is this disk here. All right. The direction of ds, it points in the x hat direction. That's the direction. And the magnitude is equal to. Now this is a cylindrical type system, right? Now I hope this is not too confusing, but this is essentially the cylindrical system, except you have x instead of z. The x-axis is pointing in the direction that the z-axis normally points. So when we were to do the integral here, the ds, the differential area element here is going to be equal to r dr d phi, just like the problem we did earlier in the class when there's a disk. Okay, we're going to be integrating over r, which is this direction here. Right, we're an axisymmetric system, so that's our r, and the x has taken place of the z. All right, so hopefully that's not too confusing there. So this is our d sub s. And so I is then equal to the integral. Oh, sorry, we forgot our limits of integration. I always like to put that down. Also, our limits of integration, we are going to be integrating from r is equal from 0 to b. Say that's the radius of the wire. And our phi is going to be equal from 0 to 2 pi. Okay, so if we do this integral, I'm not going to go through the math of it, but what you're going to find is that because J is uniform everywhere on the surface, the I is just going to be equal to J times A. All right, and this is equal to and J is equal to sigma times E sub x, and A is pi b squared. All right, so remember where this came from? J is equal to sigma times E. All right, that's what was up here as well. The area, the cross-sectional area is pi r squared, so we said this has a radius of b. Right, and the total current is then equal to this. So the last step here I'll show you is that the resistance there should be a negative sign here. Yep. So the voltage is equal to V over I. All right, this is where the electric fields actually cancel. Negative E sub x times L divided by, in the numerator you have your current, negative sigma E sub x times pi b squared. Right, so the E sub x's cancel, these cancel, and you're left with L divided by sigma pi b squared. And this here is the cross-sectional area, A. So this is where that this is where the resistance equations comes from. I'm sorry about that. Resistance is equal to V over I. So the resistance is equal to L divided by sigma times A. Right, and that's where we came up with that. Okay, so it looks like we're just out of time here. I wanted to go over the second example. We'll have to save that for the next class. Are there any questions before we stop for today? Okay, oh, Falak has a question. Okay. All right, so thanks for your attention. We'll meet again same day, Wednesday. If you have questions, please get started on the homeworks. It is a long homework, and I would like for everyone to have a chance to ask questions during class or before or after class during office hours before Thursday. Okay, the homeworks, I want you to spend a lot of time on the homework because that's what's going to allow you to really learn this material. There's only a limited amount of stuff that we can go over in lectures because otherwise we can spend hours and hours doing problems. So you do have to spend the hours and hours doing problems when you're at home, step by step, and let me know what problems that you run into. And when I post the solutions, I want you guys to go over them very, very carefully. Okay, as you know, homeworks are going to account for more of your grade now because of the second exam has been canceled. And so I want you all to spend a lot of time on that. Okay, think about all the time that you are spending in traffic going back and forth between Detroit. Just allocate all that time to integrals and electromagnetics. That would make me very, very thrilled. So have a good Monday, and I'll see you all on Wednesday. Siva is typing something. Siva, did you have anything to say? I'll take that as a no. Okay. Siva, let me know if you have a question or anything. Please email me. All right, so we'll end here. I'll see you all on Wednesday.